everyone, my name is Jun-Ting Chen, and I come from graduate program of Data Science, National Taiwan University, and Academia Sinica. In this video, I will briefly talk about our recent work, detection and classification of coronary artery plaque in coronary computed tomographic angiography, or CCTA for short, using 3D CNN. CCTA is one of the most common assessments of cardiovascular disease. However, manually detecting plaques over the complete coronary artery tree is time-consuming. Therefore, we aim to develop a fast workflow for automatically detecting coronary plaques based on the deep learning algorithm. The challenge is that collecting large amounts of CCTA scans with annotations is very difficult. In addition, the plaques only account for a small part of the coronary tree. Hence, the model tends to overfit the healthy region, which is the major class. Previously, intensity-based thresholding methods and machine learning approaches were used to detect plaques. Furthermore, a 3D CNN composed of the recurrent layer is also used for both plaque characterization and stenosis detection. In our work, we first extract the cross-sectional planes, or CSP for short, with the artery centerline information from the annotation software. And then we apply an automatic sliding process to traverse the whole arteries. Each time a sequence of 60 contiguous CSP will be stacked together for entering the 3D CNN for prediction. Then the output will be the plaque type at each plane. For CSP extraction, we first collect control point coordinate, tangent vector, and normal vectors information from the software. Then span the normal and binormal vector to get coordinate for each pixel on the plane. Finally, we will apply interpolation to estimate the pixel value. From the histogram of pixel value of extracted plane, we find that most of these values range from -200 to 600. Furthermore, a small portion is in the interval between 600 and 1200. Therefore, we design a transformation adapt from min-max normalization and value clipping to map all pixel value into the interval from 0 to 1. In this work, we modify the R plus 1D resonant architecture to design our model. As we can see in the diagram, the network is controlled by several 2 plus 1D convolutional blocks. Each 2 plus 1D convolutional blocks is composed of a spatial 2D and a temporal 1D convolutional layer. Instead of only output one prediction of the input sequence, we replace the output spatial temporal pooling in the original R2 plus 1D architecture with a 1x1 convolutional layer to output the prediction of each plane in the sequence. Each prediction of each plane will be one of the 4 classes, that is, health, soft, mixed, and calcified type. To prevent overfitting in the healthy region, we also include classes weight for cross-entropy loss and data sampling. Besides, the ADN-W optimizer and cyclic learning rates allow the model to learn more iteration without falling into some improper local minima. To evaluate our method, we collect 127 CCTS scans from National Taiwan University Hospital. These scans are split into 88 for training, 22 for validation, and 16 for testing. This scan contained 97 soft, 241 mixed, and 289 calcified plaques for all. The average slice thickness is about 0.5 and the slice shape is 512 by 512. And the average pixel spacing is about 0.39 by 0.39. In our experiment, we collect the result of detect plaques in the 17 testing cases. We have 10 of 18 soft plaque detect, and all of the mixed and calcified plaques are detected. And here is a visualization of the prediction of one test class. In this case, we can find that all the plaques are detected with some misclassified region and a small portion of false positive. From our result, we consider that this training strategy helps the model learning better on our imbalanced dataset, and our method successfully detect most of the plaques, but with some region misclassified, especially for the soft plaque type. In this work, we present an efficient workflow of automatically detecting coronary artery plaques. It takes about 25 seconds to perform the workflow, including all the preprocessing steps and prediction for each patient. In the next step, we aim to include the significance of stenosis for each plaques into the training and evaluation of the model. And we also consider lumen radius estimation on the cross-sectional planes as a valuable approach for severe stenosis detection. Thank you very much.